Hi everyone, in this video we're going to be looking at velocity versus time graphs. In a velocity versus time graph, we look at an object as it goes through a journey and we record the velocity of the object at different times throughout the journey. In the graph, on the y-axis, the vertical axis, we'll have the velocity, and that'll very often be in meters per second, but in this one on the screen it's kilometers an hour. On the x-axis we'll have time, usually in seconds, but in this example, on the x-axis, the horizontal axis, we have it in hours. There are two components to the velocity versus time graph that we're interested in. One is the area underneath the line, because that's going to give us displacement. So the area under the line gives us displacement. And the other that we're interested in is the gradient of the line, which will give us the acceleration of the body at any point. So we're interested in the area under the line, which gives us the displacement of the body, and the gradient of the line, that's the slope of the line, which gives us the acceleration at any point in time. Okay, so here we go. We've got a story. Jeanette hopped into a car at the end of a week and she drove down to a little beachside holiday spot just south of Bunbury. It wasn't a very eventful drive. Her velocity didn't change for the entire journey. She travelled at 100 kilometers an hour and she travelled for 2 hours. How far was it to a holiday spot? Now, looking at this question, how far was it to her holiday spot, you don't really need the velocity versus time graph. I've drawn one here in this slide. You can see it. It's a straight line moving for 2 hours from 100 kilometers an hour. But you don't really need the graph to figure out how far her journey was. I mean, we know that she traveled for 2 hours at 100 kilometers an hour, so that's pretty obvious. She went for 200 kilometers. Now, 200 kilometers, this is the scalar. It's got a magnitude, but it hasn't got a direction. So that's the distance she traveled. So the length of her journey was 200 kilometers, but her displacement, the vector, was 200 kilometers south. We see on the axis there, we see its velocity south, kilometers an hour south. So Jeanette traveled for 2 hours at 100 kilometers. Let's look at that graph now. We don't need the graph to answer this question, but it's interesting to look at the graph. And you'll notice that if we look at the graph, underneath the line of the graph, we've got a rectangle. And when we look at the rectangle of this particular graph underneath the line, we can see that it's got a height and it's got a length. Now the height of our rectangle is 100 kilometers an hour. It's not 100. That's not good enough. No, we say it is 100 kilometers an hour. The units matter. And the length is 2 hours. Not 2 by itself. It's 2 hours. So we've got a height and a length. And of course, we see this rectangle and we can figure out the area of a rectangle, because the area of the rectangle is equal to the height times by the length. And as we go through and we figure that out, it's 100 kilometers an hour south times by 2 hours. We end up with 200 kilometers south. The hours cancel out, leaving us with 200 kilometers south. So from this, we see that the line produces a rectangle, and the area of the rectangle is the displacement. So the area under the line of a velocity versus time graph gives us the displacement of the body over that time. So the area, in this particular one, it's a rectangle, height times length gives us the displacement. Okay, so in that previous example, we had a rectangle. It was a very, very simple example. Here we've got a news story. A remote-controlled toy car moves north along a path. Now it initially accelerates, then it cruises at top speed, and then it slows down, it decelerates. So for the first 5 seconds, it's getting faster, and then from 5 seconds to 10 seconds, it's cruising at top speed. And then from 10 seconds to 15 seconds, it's slowing down until it stops. Now, we've just said that the area under the line gives the displacement. But this isn't a convenient rectangle. This is a slightly more complicated shape. So what are we going to do? Well, the area under this shape can be broken into simple shapes. And when I look at this shape, I see a triangle, a rectangle, and another triangle. So we can break our more complicated shape into simple shapes. And then all we have to do is find the area of each of those simple shapes, find the area of each of those, add them together, and we'll get the total displacement. So we'll do that. Of course, the area of shape number 1 is a triangle, and the area of a triangle is a half base times the perpendicular height, which we go through and we say, right, well, what's the base? It's 5 seconds. What's the perpendicular height? It's 5 meters per second. We end up with 12.5 meters. The seconds cancel out. Area 2, there's a rectangle, so we've got base times height, 5 seconds times 5 meters per second, and that's 25 meters. So far, area number 1 tells us that as the car is speeding up for the first 5 seconds, it travels 12.5 meters. Then, area number 2, as the car cruises along at top speed, it cruises for 25 meters. And then area number 3, as the car slows down, it covers a distance of 12.5 meters. Now, if we add these 3 values together, we end up with 50 meters as the distance traveled by the car. Its displacement is 50 meters north. The area under the line gives us the displacement. Okay, what about the acceleration? Here we go. The gradient gives us the acceleration of the object at any point in time. So we look at the gradient. Now, if we look at 3 seconds, we see that this journey is broken up into 3 parts. For the first 5 seconds, we're accelerating, we're getting faster. For the second 5 seconds, we are cruising. And then for the final 5 seconds, we are slowing down. So at 3 seconds, what is the gradient? Well, of course, gradient of a line is rise over run. Now, I look at the line between 0 and 5 seconds, and it's rising as we move to the right. So it's got a positive slope, rise over run. What is the rise? Well, it goes from 0 meters per second up to 5 meters per second. So the rise is 5 minus 0 meters per second. The run is 5 minus 0 seconds, because this happens over 5 seconds. So 5 divided by 5 gives us 1, and meters per second divided by meters per second divided by seconds gives us meters per second per second. Meters per second divided by seconds gives us meters per second per second. The gradient gives us the acceleration at any point in time. So we've got rise over run, is our gradient. Okay, fantastic. What about the middle 3 seconds, from 5 to 10 seconds? We see it doesn't rise at all. So the rise is 0. So the gradient is 0, which means the acceleration is 0 for the middle part of the journey. And for the final part of the journey, when we go from 10 to 15 seconds, it doesn't rise, it actually falls. So it's a negative rise, which indicates that it's a negative acceleration, which means that it's slowing down in this particular story. All right, the gradient gives us the acceleration at any point in time. From this, we get the acceleration equation. In Year 10 physics, we have the acceleration equation is equal to the change in velocity over the time it takes. That comes exactly from the gradient equals the rise over run. Gradient is acceleration, rise is change in velocity, run is the time that it takes. So what else can we do with these graphs? We can read the instantaneous velocity off the time graph, velocity time graph. That's easy. So for example, at 13 seconds, we're moving at 2 meters per second. And that's velocity versus time graphs.